Hello friends, today we will talk about the multivariate LSTM. So I got a request to talk about the multivariate LSTM where the LSTM is famous because like all the regression model, they can do the time series prediction on the univariate dataset. But LSTM can do it on the multivariate dataset. And it is very much practical also to do the time series prediction on the multivariate dataset because your output data or output data set is actually like in fact depending on several factors. So in this case, I have taken a very simple data set. So before starting this video, I would say thank you to Jason Brownlee because he has a very interesting blog and sharing tremendous knowledge in this data science and machine learning. So you can always refer to his blog. I am giving the link of this reference in my video. You can check it. And I just influenced by the data set he has used. So you can take it from directly from his blog, or you can download it from the this repository, that UCI repository. So this is an archive of like very popular data set which is used for the research purpose or the project purpose, very small POC purpose, time series prediction model. And this is like a Beijing parts per million 2.5 micron. That is like a indicator of how purified or how much polluted your air is. So this is a uh, data set of the city Beijing. So it's very infamous for like air pollution. So this is like what are the several factors contributing to the air pollution in Beijing, and what could be the air pollution for 2.5 micron or small particles, and what is its quantity in parts per million in the air. And this other data fields which is contributing to it is like a it is like row number, year, month, day, and hour, and like the ppm 2.5 particles, and what is the dew point, and what is the temperature both in Fahrenheit scale, and what is the pressure, and what is the wind direction, and what is the mm, like wind speed, and what is the hours of snow and hours of rain. So this is a data set what I have used, and this is like a hourly data set. So these first four fields I can actually accumulate to create the first four field. I can accumulate to create the timestamp of this each row of this data set. And the first field is actually not required, so I will remove it from my data set. And these are my actually input features. So the number of it is actually 8. So these are the 8 feature, and this is the time field. So I will create the timestamp field from it. So bear me with my writing because I'm using mouse only. So this is my, like, I can write it in like this. So this is my timestamp field, and these are the 8 input features we will going to use. So let's start today's video. And at the end of the video, you will know how can you predict a multivariate data set using the LSTM model, and what are the different steps you need to do it. And this is not a fine-tuned prediction you can achieve. I just give you like a base to start, and you can always do some kind of modification and some kind of addition, alteration to get the accurate result. So to save the time, I just give you the only the basic version of it. Let's start. So this is the data set, and I will just remove this number, this row number, and I will like get all these four fields to create the timestamp, and these are my data fields, actually the input features, you can say. And you see wherever there is a missing data, so that data is actually denoted by NaN. So I can just take those data, and I can remove it from the data set. So, and like you can see, the most of the fields or most of the features are actually numerical features. Only the wind direction is actually a categorical feature. So I need to change it using either a level encoder, or you can change it using the one-hot encoder. I have the several video to explain fully about it, but we'll use the level encoder here, though you can use the one-hot encoder as well. So let's proceed. And I just drop the NO feature because it's of no use for my purpose. And then I just drop the missing records. So missing records is only actually present in parts per million 2.5 feature. So I have removed it from that feature only. And axis is equal to 0 means that column wise drop, not the row wise. Row is axis is equal to 1. So you can take note of this small wisdom, or good to know points. And now the data is looking like this. So you have removed the NO feature, and you have removed all the missing records from the PM 2.5 feature. And next thing you need to do, actually, you need to accumulate all these four fields, like year, month, day, and hour, and you can create a time. So this is like how I did it. You can use other method to parse it as well. And once you have done it, you can see that now these are all your features, and this is your timestamp. So I have given the name timestamp to this feature, which is the accumulated feature of these all four times related features. And let's proceed. And now I will create this timestamp as my index field, so that I can proceed further. And because it is required to create the timestamp field as an index field. So now the timestamp field is an index field, and this is an hourly data. You can see like this data is starting from, like you can see that year 2010 and month 1 and day 2 and hour 0. So this is the same is actually reflecting here. So let's proceed. And now I will plot this data using the matplotlib, and I just get like what are the number of columns. So this will give you like value 8, and I'm starting from the index 1, and then like this is like the subplot I have used. So if you create a subplot, it will be like, if you want to create a subplot like this, so you need to create like row is equal to 2 and column is equal to 1. So this will be like row is equal to 2 and column is equal to 1. So the same theory I have used here, and like I have given the number of columns. So number of columns will be 8. So there will be 8 rows. Row is equal to 8, and number of column will be 1. So C is equal to 1, and this is the index, like what is the number of this particular plot. So for each plot, I have given like each feature. So this is feature 1, and this is feature 2. The same way I proceed till all the 8 features. So let's proceed. And this is how your plot will look like. And you can see there is some seasonality of this data. I will not remove this seasonality. I'll proceed as it is. And let's just convert this categorical data to the numerical data, and then I will apply the LSTM model using the Keras package. So only the field combined wind direction need to transform from categorical to numerical. So for that, I have used the level encoder because this is the simplest to use. And I just get this index data and change it to like encoded to like there are like 4 directions, so it will be like 0, 1, 2, 3. So let's proceed. Now you see that combined wind direction will be like having some numerical value. Now if I just this plot again, so I have given like several colors for your identification, so you can use it or you can like use it like simple like this as well. So I have given like different color for you. So now my plot is ready, and you can see that combined wind direction is having like 4 values, 0, 1, 2, and 3. And the rest of the plot is having some kind of seasonality, you can say. And there is some trend part as well. So let's go to the next data. Yeah. So like mostly I can see there is seasonality and the randomness. So let's proceed with this data. And I just need to scale this data before applying LSTM. Why? Because the activation function like hyperbolic tan function, these functions actually very sensitive to the scale of the data. So if the scale of the data varies for all the features, this will give you very bad result. So you cannot expect a very good prediction out of your LSTM model if you don't scale your data. So I have used a very simple scaler like min max scaler, and I have used the default range, and I just scale this data, and this data is looking like this. I just printed for your own understanding. So this will now look like this. It's not having like different range, as you can see in the above pictures. So it is having like different range. And my job is now to predict this, what will be the parts per million 2.5 micron particles in the like test data. So first I just, you know, distribute this data into train and test data. And like train size is like 90% of the data, and the test size is like 10% of the data. And now I have two data set. One is called train and another is test. Now from the previous video, you know, like I need to create a shape out of this data. So you can create the shape by your own written function or any custom function you can write, or you can use like one Keras time series generator, which can automatically generate based on your past lags and the number of features. So I have given like the number of past lags, so you can like vary it. I have explained it in my previous video where I have explained the LSTM for the univariate data set. So there you can actually change this number of lags. So this is like number, how many past values you are depending upon to predict the future. So it is like t minus 3, t minus 2, t minus 1, and now the predicted data is t. And next, when this will be like your past, then you are predicting actually t plus 1. So this is the like whole point of doing this kind of uh, shape conversion. And number of features you already know from the data set that you need to use the number of features equal to 8. And now this data set will look like, so I have done it for both the train data and the test data. And if I just print this, the data will look like this, like these all features will be given in one array. and the output, the next t timestamp. So these are all this is t minus 3. So I can draw it. So this is actually t minus 3. This is actually t minus 2. And this is actually t minus 1. You can check it from the data set as well. And this is actually the current data set, like t. So in this way, actually, the dataset shapes is generated, and I need to use the same kind of shape for fit and prediction. So for fitting data, I just use like the LSTM, and what I need to define. So for LSTM, so any like neural network, so you can have like 3 layers, right? So one is the input layer, one will be the hidden layer. So this is your input layer, this will be your hidden layer, and this will be your output layer. So you can define what will be the number of neurons you can define between input to hidden layer, and what will be the number of outputs. Okay, so I have given here like what is the like number of neurons. So this is defined between the like input and hidden layer, and the activation is a hyperbolic tan function, and the input shape is this is the number of past or lags, and this is the number of features, and this is my input shape. And like dense is actually defining what will be the number of output. So that is the number of features. So n features is equal to 8. So the number of output will be also 8. So this is 8 and this is 50. Now for compilation, I have used like Adam optimizer. This Adam optimizer is actually a stochastic gradient descent method to optimize, and this is like loss function is the mean squared error function. So I have used these two for compilation, and then I have used the train data for fitting data, and I have used only 5 epochs. So you can increase this number of epochs. Okay, and I have used the batch size as 72. So so using the multiple feature, it will actually take some time. So I have just run it using this model definition, and then I just need to predict the data. So for prediction, I have used a empty array, and then I have used the last 3 data set. So I need to predict from the test. So for the train data, I have used the last 3. So t minus 3 I have taken, and t minus 2 I have taken, and then t minus 1 I have taken. So this is my like last 3 input from the train data set, and I have created the current batch out of it using this reshape function. And then like for each iteration, I need to like predict it, and I need to remove like one data from this set or this batch, and I need to add one data into it. So this is how it is. So first I'm like predicting it, and then I just append this prediction to this prediction array, and then I just remove the t minus 3, the first one from this whole array, and then I append the new prediction to this array for the next prediction or the next batch. So this is how it is iterated, and like the number of test feature I have iterated it, and because I need to compare it with my test, and then when this prediction is done, actually I am comparing this data with the prediction data with the test data. So for this, I have actually taken all the data set, but I am using the first feature only. The first feature is actually PM 2.5. So I have taken both first feature both from the test data and the predicted data. And then I have plotted it. So you can see this is not a very good prediction because it's not following the actual test data. Yellow one is the test data, and this blue one is actually, that predicted data, but it is going in between. So like it is like a average. And by taking the mean squared error also, you can see like it's not creating a very good prediction. So the mean squared error is very high. So you can actually fine tune this prediction by changing by like first you can remove the seasonality, or you can like fine tune the definition of the LSTM model. But merely you need to follow these all steps to achieve any prediction from your multivariate dataset. Thank you for watching this video. Please let me know if you want to know more about any other model in this time series forecasting series. In the next video, I'm going to cover the VAR method of time series prediction model. Please stay tuned. Thanks for watching.